Welcome to our lesson on inferences from two sample means when we have independent samples. In this lesson, we're going to look at the methods used for doing confidence intervals and hypothesis testing when we have two different samples and those two samples are independent. Later on, we'll be looking at how to deal with two dependent samples. So in part one, we're going to look at kind of the more common, more realistic of the situations where the standard deviations of the two populations are both unknown and are not assumed to be equal. In part two, we'll just briefly look at the other situation, the other two situations, in fact, where one, the two population standard deviations are known, which is very unlikely, and two, the two population standard deviations are still unknown, so we still don't know what they are, but we assume them to be equal. And because we normally don't know the standard deviations, and because it's normally not a good idea to assume they're equal, the techniques in part one are going to be the techniques you would use most often in a real world situation. So let's start with that. Part one, independent samples, both the standard deviations, right, sigma 1 and sigma 2 are unknown, and we're not going to assume they're equal. All right, well, first we need to discuss what does it mean to be independent versus dependent. Two samples are considered independent if the values selected from one population are not at all related or somehow paired up or matched with the sample values from the other population. And then two samples are considered dependent if their values are somehow paired up or matched. So, for instance, two measurements from the same subject. If you did before and after weights, or before and after cholesterol levels, right? Or a pre-test, post-test, anything like that where each individual, each subject was measured twice, then the set of all the pre-test scores and the set of all the post-test scores, right, would be considered dependent samples. Another type of dependency would be if you were testing two different objects, but those objects are somehow related. So if you were looking at IQ scores of husband and wives or any couple, right, those two people are matched, and so looking at their IQ scores is now paired data. Or if you looked at, let's say, IQ scores of siblings, brothers and sisters, also matched data. So those are the two kind of most common instances where your data would be considered dependent. We're going to look at independent stuff here. So a good example, researchers investigated the reliability of a test assessment. One group consisted of 30 students who took proctored tests, and a second group consisted of 32 students who took online tests without a proctor. Now we know these two samples are independent because the subjects aren't matched up, right, or paired up in any way. You know, it's a different set of students in one group and a different set of students in the other group, so we weren't measuring the same students twice. And they're not matched up because there's no logical matching between them. You know, it's not like group A were all the siblings of group B or something like that. Here's a dependent sample, or a dependent example, heights of husbands and wives. So there's an obvious kind of pairing between the set of people from both samples. Typical notation, right? We're dealing with means now, averages of populations, and we're dealing with means of our samples. So we're back to doing mu and sigma, only now because we're dealing with two groups, everything has to have subscripts. So mu sub 1 and sigma sub 1 are the mean and standard deviation of the first population, and then mu sub 2 and sigma sub 2 would be the mean and standard deviation of the second population. Same goes, of course, for n and x bar and s, right? So all the same symbols we're used to, only now we have subscripts because we have two different groups. Okay, requirements for this test. Sigma 1 and 2 have to be unknown, and no assumption is made about the equality of them, right? That's the big key thing that we're doing now. The two samples have to be independent. Both samples have to be simple random samples. And then we're kind of back to that same condition we had before, where we have to either be sampling from a population that has a normal distribution, or we have to make sure our samples are large enough, in this case over 30. And just like we had to do that when we were dealing with one sample, we now have to have those conditions met for both samples here. Our typical test statistic for when we're dealing with two means, again, because we don't know the standard deviation of the populations, we have to use a t-test instead of a z. If you don't recall or don't have it readily available in your notes, just to refresh your memory, the t for when we're dealing with just one was simply x bar minus mu all over s over the square root of n. Can you see the correlation between these two? Can you see how similar they are, right? The top of this one is all about the difference between our sample measurement and the population we're comparing it to. Here we're looking at the differences between our two samples and comparing it to the differences between our two means. So we still have that deviation score, right? The difference between the populations and the samples. And then down below, look at this. It's the variance of the first group over n plus the variance of the second group over n, and then the whole thing is square rooted. Well, if we took this bottom, couldn't we just write that as s squared over n and then have the whole thing under the square root instead of just n, right? Because then it would just be the square root of s squared and we'd be back to s. So can you see the correlation? Very strong relationship between these two formulas. They're very, very similar. When we're dealing with independent samples, our degrees of freedom are not easy to calculate by hand. If you had to do something by hand, you would just say the degrees of freedom is going to be the smaller of the two. So the sample size of one group, right? One sample minus one or the other sample minus one, whichever one is smaller, that ends up being your by hand version of degrees of freedom. However, we're going to be doing all of this with technology, and it will give you the actual precise degrees of freedom, which is calculated using a very complicated and complex formula that you don't need to worry about. P-values, just like before, we'll try and get them out of technology whenever we can, and we can always get them here. We can also get them most of the time out of tables. And then critical values, we have to look up most of them in a table, although some technology can give them to us as well. The formula for our confidence interval, very similar to the formula for a confidence interval, for one mean, which if you don't remember, it's very simply just x bar, right, minus your margin of error is less than mu is less than x bar plus your margin of error. You can see the parallel nature, right? Instead of x bar, we're looking at the differences between the two means, and then instead of dealing with just one population mean, we're relating it to the difference of the two population means. So very similar again. Also, the margin of error that we calculated for one sample was still your t of alpha over 2, and then it was times s over the square root of n. But again, just like before, isn't that the same thing as s squared over n, the whole thing square rooted? And then you can see how these two formulas are extremely similar as well. Also, as we stated before, if you have to do this stuff by hand, you always pick the smaller of the two to be your degrees of freedom. If you're doing it with technology, you don't have to worry about that. It calculates degrees of freedom for you, and it's just going to ask you for sample sizes. Now, before conducting a hypothesis test, we always have to consider the context of the data, the source of the data, the sampling method, all those types of things. We should do some basic descriptive statistics and display our stuff just to verify that all the requirements are satisfied. Here's a simple example. So some researchers conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for a brick, while another group of subjects were given the same task, but they had a blue background around them. Responses were given by a panel of judges, and then the researchers make the claim that blue enhances performance on a creative task, and they want to test the claim using a 0.01 significance level. Check our requirements. The values of the two population standard deviations are unknown, and we don't assume them to be equal because we have no idea what the population standard deviation, of people trying to find out creative reasons or creative uses for a brick would be in either group. The two subject groups are independent because we just randomly put people in the two groups and then there's no relationship between them. It's not like we took twins and then split them. The samples are simple random, right, because we randomly assign them. And then both sample sizes are over 30, so we don't have to worry about whether or not they come from a normally distributed population. So we're good to go. All requirements are satisfied. Here is the data collected from the two groups, 35 in one group, 36 in the other. The one group had an average of 3.39 creative uses for their brick, and the other one had 3.97, and then the corresponding standard deviations for those two groups. Step 1, identify our claim and write our hypotheses with the proper symbols. So the claim was that blue enhances performance on a creative test. So we can think of that as people with a blue background, i.e. what we're going to call group 2, have a higher mean creativity score than those in the group with a red background, group 1. Or in other words, the average number of creative uses from group 1 is going to be less than the average number of uses from group 2. And so if that's our claim, the opposite, right, has to become the other side of the argument, which is what we just write as an equal part for our hypotheses. And then of course our claim ends up being the alternative. Again, that's not the rule, right? The claim doesn't have to be the alternative. It's just better if you can make the alternative your claim, because then you're now testing a stronger argument. You get a stronger result. But that's not what has to happen. What has to happen is the null has to be the equals part, and then the alternative always has to be the less than, the greater than, or the not equals part. Okay, step 2, select your significance level. In this case we were told it was 0.05, and then step 3, determine your sampling distribution, calculate that test statistic, and the corresponding p-value. Well, because we have two independent samples and we're testing a claim about two population means, and we don't know the standard deviations of the populations that we're dealing with, we have to use the t-distribution. And then we use the corresponding test statistic that we saw earlier, plug everything in, and get a test statistic of negative 2.979. Because we're using that t-distribution, we can also figure out the critical value on the curve using technology or a table. If we use a table, we would have to use the smaller of the two samples version, which was 35, and 35 minus 1 gives us a degree of freedom of 34, and then we get our critical value of negative 2.441. The p-value associated with the test statistic that we got of negative 2.979 is 0.0021. Now if we were doing technology, we wouldn't even bother with doing the critical value. We would just have this information from technology, and that would be all we would need for the p-value method. Step 4 is we have to make our decision, because the test statistic does fall in the rejection region, right? We reject the null hypothesis, and the p-value gives us the same result because the p-value is less than the 0.01, right? It was 0.0021. So both methods will always give you the same result. In this case, they both tell us to reject the null hypothesis in favor of the alternative, which means we now have step 5, to restate it in normal wording, significant evidence to support the claim, right? Because we're now rejecting the null in favor of the alternative, and the alternative was our claim. So we have significant evidence to support the claim that the red background group has a lower average creativity score than the blue background group. Okay? We can also use the data from this example to construct a 98% confidence interval estimate for the difference between the mean activity score for each group, those that had the red background and those that had the blue background. We could use the formula and plug everything in and get this confidence interval as being the difference between the two groups. And you can see that this is saying that the difference between population 1 and population 2 is always between, well, not always between, we did a 98%, so we're 98% confident that it's between a negative 1.06 and a negative 0.10. Even though that's really close to 0, it doesn't go up and include 0. So 0 is not in this interval, and because 0 is not in this interval, we're 98% sure that the difference between those populations doesn't equal 0, which again gives us that same result of rejecting the null. But we really don't want to use confidence intervals in that way. It's the weakest of the three ways to test it. But this is what's, saying what we just talked about, that because it doesn't include 0, our interval also suggests that there is a significant difference between the two. On to our alternative methods. And this is when we have the weird, the rarely used situations where either one, the two population standard deviations are both known, and then in that case we'll use a z instead of a t, or case 2, the two population standard deviations are still unknown, but we assume them to be equal, so we're still using a t, but we end up pooling our sample variances. Here's the corresponding test statistic for when the two standard deviations are known. You'll notice it's exactly like the old one, except instead of s sub 1 squared and s sub 2 squared, we're just using the two sigmas, and instead of a t, it's now a z. Here's the confidence interval for that situation. Again, a z instead of a t, and a very similar calculation. Instead of s's, we're using sigmas. And then for the other situation where we once again don't know sigma 1 and sigma 2, right? The population standard deviations are unknown, but we're now going to assume them to be equal. It's kind of a silly thing to do, but sometimes it's done. We're back to using a t because we no longer know the population standard deviations, but instead of having s sub 1 squared over n sub 1 and s sub 2 squared over n sub 2 like we had in the other formula, we have this s sub p, this pooled standard deviation, or in this case pooled variance because it's being squared. And here's the formula for pooling it. It's kind of the same idea as the pooled p that we saw in our previous lesson about proportions. We're just assuming that they're both the same, and so therefore we put it all together and kind of get the overall grand variance of the whole thing. And then the degrees of freedom, again, because we're assuming that the variances are the same, we can just put the two samples together and then subtract 2 from it, and that gives us the degrees of freedom. Here's the corresponding formulas for calculating our confidence interval in this situation. And then here's our decision tree, right? If we know what sigma 1 and sigma 2 are, i.e. we know the standard deviations of our populations, we use the normal distribution, the z curve, with that standard deviation formula. If we don't, and we can assume they're the same, then we use the pooled method. And if we don't know what they are and we don't assume they're the same, then we're down here with the method that is usually used most often, right? This is the method that we almost always use. Okay, pretty simple formulas. Let's see how we can do it with technology. Here we have our data and our results from the formulas, right? The formula way. And then let's see how that compares to technology. Very simply, we're going to the same place we're doing all of these, right? Stat tests. And now we have two sample, right? Two sample Z and two sample T. We would do two sample Z if we knew the standard deviations of the populations, and since we don't, we're doing a two sample T. If we chose from data, then we would have to have the raw data in our lists, but we're going to do it with stats, meaning that we have the results. And so now it's just a matter of filling everything in, which I've already done. All right, so we've got 3.39 for the mean, right? Standard deviation, sample size, blah blah blah, and then our alternative hypothesis was that group 1, the way I typed everything in, right? This is group 1, the first one. Group 1 is supposed to be less than group 2, so that's why I chose that one. The next thing it asked you is pooled, yes or no, right? So this is where if you were doing the techniques from the less likely one, where you assume they're the same, then you would pool your standard deviations. But we're going to say no, we're not going to pool them, and then we just calculate. Here's the same test statistic, right? Negative 2.979 if we round to 3, and then the p-value 0.0021. So we get the exact same results. If we want to do our confidence intervals, back to the same place, only now we're doing a two sample t interval. Again with stats, the nice thing about this is it keeps all the data that we plugged in before. We just have to tell it our confidence level, which was 0.98, right? We did a 98%. Again, it asks us to pool or not. We're going to say no, and then we're going to calculate that. And here are the results. Look at how they're slightly different. In fact, I wouldn't even call it slightly. It's off by a bit. Negative 1.046 instead of negative 1.06, and negative 0.1142 instead of negative 0.10. The reason why our results are different from what they got is two main reasons. One, look at our degrees of freedom, right? It uses the actual true calculation for degrees of freedom, and it gives us a degree of freedom that's a decimal. Whereas the example in the slides was using formulas and the more conservative degree of freedom, which is just the smallest sample minus 1. So their degrees of freedom were 34, whereas ours are 58.11. The other main difference is when they calculated their confidence interval, they used t-values from a table, whereas this is all being calculated electronically, so you're getting more accurate numbers. You're not rounding as much. So the technology is always better, but unfortunately, if my math lab, asks you to use tables and formulas, and you do with technology, and you type these numbers in, it's most likely going to tell you you're wrong every single time. So just keep that in mind, that you will get slightly different answers out of technology than tables because of the difference in the degrees of freedom and the rounding errors that happen when you have to find values in tables versus letting technology find the precise values. Same goes for StatCrunch. If we did StatCrunch, we're doing t-statistics with two samples, right, with summary, and we put in all the information here, 3.39, 0.97, sample size of 35. The second one's going to be 3.97, 0.63, sample size of 36. Here you want to not pool, right? So untick that so you're not pooling your variances. And then our hypothesis test in general is that we think the two means are equal. Here we're checking that the first group member is less than the second group. Compute that. There is the same t-statistic and p-value that we got before. We want to do confidence intervals. Again, t-statistics, two samples, summary, right? Got to put all this stuff back in, unfortunately. 3.39, 0.97, 35, 3.97, 0.63, 36. Again, we don't want to pool our variances. We're doing a confidence interval this time, a 98% confidence interval, and if we compute that, we'll see that we get numbers just like we did out of the calculator, the negative 1.045 blah 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 instead of the 0.06, right, and the 0.1142 instead of the 0.10. So the technologies are the same, and they're both going to be equally different, right, from the ones you would get out of formulas. So again, keep that in mind. If a question asks you to use formulas and tables, you might want to try it, because the formulas are pretty easy anyhow. Because otherwise you're going to get frustrated when you do it in technology flawlessly and get the actual precise answer, and my math lab, my stat lab, is looking for a different answer because they're using tables. Okay, that's everything we need to know about figuring out how to do inferences about two means when they are independent samples.